Hey guys, how's it going? Mike coming back at you here with another video on Calculus 1. In the previous video, we did some sample problems regarding the extreme value theorem. We saw some examples where we can and can't use that theorem, and when we could use that theorem, we went through the process that we use to find those minimum and maximum values of our given function over our given interval. In this video, we're going to take a look at the other big theorem that relies solely on continuity. So what is the other theorem that relies so heavily on just continuity? Well, the theorem has a very apt name once you see what the theorem itself says. The theorem is called the intermediate value theorem. And here's the statement of the intermediate value theorem. It says, let f of x be continuous on the closed and bounded interval a comma b, and let d be any number between f of a and f of b. Then there exists some c value that's between a and b, could be one of the endpoints as well, such that f of c is equal to d. So what this theorem is saying is you have a function f of x, you have a closed and bounded interval a comma b. Take a, plug it into f of x, take b, plug it into f of x. You'll get two numbers. If you pick any number between those two numbers that you just found, as long as your function is continuous and your interval is closed and bounded, there is going to be some c value, some x value called x equals c, between a and b, such that when you take that x value and plug it into f of x, you're going to get that number that you chose. And here's a little sketch of the concept. This is more of a visual proof. It's not a formal proof of it, but I think that this visual proof really hammers it home more than the actual proof, and it's a lot easier to understand. And this visual proof is going to actually rely on the pre-calculus definition of continuity, which is essentially saying we can draw the graph of our function without lifting up our pen or pencil or marker. So I have my x and y axes here. I have 2 points which I drew. It doesn't really matter which one is higher up than the other. One could be positive, one could be negative, they could be both negative, they could be both positive, whatever. But I have a comma f of a and b comma f of b here. This is going to be a closed and bounded interval. Both of our endpoints are finite numbers, and we're going to assume that we're working over a closed interval here. Because we're assuming that the function is continuous over this entire interval, one of our hypotheses of this theorem, because it's continuous, I can draw the graph that goes from a comma f of a to b comma f of b without lifting up my pen. And it doesn't matter what the curve looks like. It could look like that. 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 It could look like any number of things. But what's happened between these 4 functions, which I just drew, is that for every single one of them, I did not lift my pen up as I drew this graph going from x equals a to x equals b. Therefore, for every y value between f of b and f of a, my pen hits that height for some x value. So you can check now, if you choose any y value here between f of a and f of b, and if you draw a horizontal dashed line, you can see that it intersects every one of these graphs at some x value, and the x value lies between a and b. It's It's not necessarily going to be the same x value, but there is some x value here. So this is just the basic sketch of the concept of the proof of this theorem. I think it's a really nice, easy thing to understand for Calculus 1 students. So let's go into some actual problems where we would use this theorem. So first one here, consider f of x, which is 2x cubed minus 5x squared plus 7x plus 2 on the interval -1, 1. Does the intermediate value theorem, or IVT for short, guarantee that there exists some c value between -1 and 1, such that f of c is equal to 2? Is there a c value guaranteed such that f of c is equal to 10? Well, our function is a polynomial. Polynomials are continuous for all real numbers, so they're continuous on the interval that we're given. And our interval is closed and bounded as well. Both endpoints are real numbers, and both brackets on the endpoints are square brackets. So the hypotheses of the IVT are satisfied. So what we're going to do is we're going to take each of these endpoints, -1 and 1, we're going to plug them into our function f of x, and we're going to see what we get. So when you do that, you find that f of -1 is -12, and f of 1 is 6. So what the IVT tells us is that if I pick any number between -12 and 6, I can find some c value between -1 and 1 such that f of c will equal that number which I chose. So the real question is here, we were given 2 and 10. Which of these numbers falls between -12 and 6, and which ones do not? If our number does fall between -12 and 6, then we are guaranteed that there is a c value. If the number does not fall between -12 and 6, then we're not necessarily guaranteed that there is a c value. Well, last time I checked, 2 falls between -12 and 6, so the IVT does guarantee that there is a c value such that f of c is equal to +2, but 10 is not between -12 and 6. So the IVT does not guarantee that there is a c value such that f of c is equal to 10. So this is a very basic, very low-level kind of theorem. There's really no complex process going on when we're solving problems using this theorem like we did for the EVT. Now this is, in the grand scope of things, this is a less common type of problem that we see with the use of the IVT. What's one of the more common uses of the IVT? It's really used to help us locate roots of functions within some interval of x values. We can use this guy to help us say that, okay, we know that between this x value and this other x value, we have a root of our function somewhere. And we're going to specifically state this case of the IVT because it's used often enough that it's worth noting. So here's IVT for the use of locating roots. You're given a function f of x, you're given some closed and bounded interval a comma b. If f of a is positive and f of b is negative, or vice versa, f of a could be negative and f of b could be positive, just as long as they're opposite signs. And if your function is continuous on the closed and bounded interval, then the IVT guarantees that your function f of x has a root between a and b. If f of a and f of b are the same sign, either both negative or both positive, then the IVT does not guarantee that there is a root between x equals a and x is equal to b. So if when you plug your endpoints into your function, you get different signs, you're guaranteed a root. If you get things that are the same sign, then you're not guaranteed a root. So here's a sample problem to see how we use this version of the IVT. Our given function is x to the sixth minus 4 times x to the fourth plus 3x cubed plus 2x squared minus x minus 9. Does the IVT guarantee that f of x has a root on the interval 0, 1? Does the IVT guarantee that f of x has a root on the interval 1, 2? All right, well, these are both closed and bounded intervals. Again, we're working with a polynomial, so this is continuous everywhere. So the hypotheses are going to be satisfied. For the most part, when you're working with these kinds of problems, you don't typically have to worry about the hypotheses being satisfied. At least anything that you see from me, you're not going to have to worry with it so much. So what we're going to do is we're going to plug each of these endpoints into our function, and we're going to see what values we come up with. If I plug 0 into f of x, I get negative 9. If I plug 1 into f of x, I get negative 8. And if I plug 2 into x, or into f of x, excuse me, I get 21. So first question that we were asked here, does the IVT guarantee that f of x has a root on the interval 0, 1? Well, f of 0 is negative, f of 1 is negative as well. We just said when the signs of both numbers are the same, either negative or positive, you are not guaranteed a root. All that the IVT guarantees is that if you pick some number between negative 8 and negative 9, then there is some x value between 0 and 1 such that f of that x value equals the number that you chose. So our first sentence here, exactly what we just said, since f of 0 and f of 1 are both negative, the IVT does not guarantee a root between those two x values. If we look at the interval 1, 2, we see that f of 1 is negative and f of 2 is positive. These things are not the same sign. So when your quantities are not the same sign, when one's negative and the other one's positive, the IVT does guarantee a root between those two x values. So the IVT does guarantee a root between 1 and 2. So this is just one common use, or one of the more common uses of the IVT here. Now there's a really important thing that you should note about what the IVT is saying. The IVT only tells us when we're guaranteed a value. It does not say that it's not possible to have some value happening. This theorem says you are guaranteed to have this guy provided it's between these two numbers. It does not say that if this number is not in between these two things, then you don't have an x value out there whatsoever. Specifically, in the more common use of using the IVT to locate roots, the IVT may not guarantee a root inside of an interval, but you could still actually have a root there. It's just that this theorem does not guarantee that you have it. We're going to look at a fairly trivial sample here. For example, if you take f of x equals x squared, and you look over the interval negative 2, 4. Now we know that if we plug 0 in for x, we're going to get 0 out. And that means that x equals 0 is a root of f of x here. But if we just go by the hypotheses and conclusion of the intermediate value theorem, f of negative 2 is 4, f of 4 is 16. So all that the IVT tells us is that if you pick some x value between 4 and 16, I can come up with some x value between negative 2 and 4, such that when I plug it into f of x, I get that number that you chose that was between 4 and 16. So the IVT, just like the EVT, only tells us when we are guaranteed to have something. It doesn't help us rule out things. It just only tells us, yes, you definitely have it, or you may still have it. And there is a process for solving problems which are associated with that particular theorem. In the case of the IVT, your process is a lot quicker and a lot easier. EVT, a little bit more complicated. So this is the end of our video on the intermediate value theorem, a couple sample problems, as well as what this theorem is actually saying. In the next video, we are going to get into a couple theorems that rely not only on continuity, but on differentiability as well. One of these theorems is arguably one of the most important theorems in all of Calculus 1. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy.